Okay, year 13. One final part on X-rays, much more brief this time. So what we're going to do for this section, which is actually section 2, is more of a descriptive level. So not the description of how things work, not the mathematics to do with all the different attenuation mechanisms, i.e. the things that reduce the amount of intensity going through the patient, for example, or whatever it is you're x-raying, but actually how do we get a better image out of it. So for the course you do not need the detail of the detectors, etc. However, we use a similar system for gamma ray and nuclear radiation imaging, so we'll look at that in the next section. So we're really just going to look at kind of some basics here, some very quick basic ideas. So the first bit is really that we do want to base things around the kind of the mechanisms that cut down on the intensity and how we can change those. So as I said in the first video, you can reduce the voltage on the X-ray tube, and that softens your X-rays. And a soft X-ray is ones that are working at lower frequencies. So if there are lower frequencies, they're not as penetrating, and therefore they're better if you want to image what's going on in soft tissue. Now, any soft tissue in the body still has issues in that they're not much different. You can't differentiate much between where there is connective tissue, or you've got your muscle in the guts, in the stomach, for example, as compared to the tubes that effectively go in and come out. So the different structures within the body aren't easy to see. So what we can use is we can improve it, which is the point of this chapter. And to improve it, you can use various different things. So we can look at a different type of X-ray system called computerized axial tomography. Okay, tomography just means to map out, so to give us a graphical image. So not just a picture, an image, but one that has a spacing attached to it. So that graph of its position against the image. So build up three-dimensional images, basically. But before that, there's a more simple system, which is actually looking at changing the medium it's going through. So I don't mean changing the body, but adding things to the body. So contrast media is something you need to know about, and it's a fairly common system. You might even have had it or know someone who's had this. So what we tend to do is use something like barium meal or other materials. Again, if we go through here, you've got iodine mentioned as well. Both of those aren't too chemically reactive with the body. They don't cause much harm, but there's something that passes through your body. You can inject in it, you can ingest it, so you can drink it in a drink called a barium meal, because it feels rather full and thick. And what it's done is, the design of it is it absorbs a lot of the X-rays, so it has a high attenuation coefficient, which means that things stand out a lot more obviously. So if we look at my slightly dodgy picture here, here's an image, fairly obviously bone. You can see where the bone is densest, where the X-rays have had to go through the thick edges and so on. So this is quite high energy. It's not giving a very definite shadow. You know, it's contrasting across here. Normally you wouldn't see much going on inside the soft tissue, large intestine that we've got here, and small intestine first, and the colon, etc. But this shows it absorbing a lot, and this is because you have this barium meal. Okay, so that has a high value of attention coefficient, the mu, okay, in the calculation. And because you got a high mu, you don't need much thickness to do it. What's the point of this? Well, the point is not just you can see up the soft tissue, where the soft tissue is, but you can also look for where there are problems, where there's blockages or where there's too much building up, maybe some constriction within tubing, etc. Okay, so contrast material is quite common. We use it in engineering as well with imaging, but for the human body, the most obvious is if you're trying to investigate the digestive system. Okay, so that's one area that you need to know about and be able to describe how it does it. The key is it links in with the mathematics, so it's that high value of mu in the intensity equation, the half thickness equation, shall we say. Okay, the other one is much more common, and it's one of those things that you do need to know your way around a little bit, because effectively it has a person who goes into a tube on a tray, happy, smiling, etc. And they all look the same, these machines. So giant, expensive looking tube, noisy machine, that kind of thing, you're slid in, they all look the same. Now a CAT scan is still basically an X-ray machine. Okay, so what we've got going on is that instead of our normal system where we just have a fixed head and you fire the X-rays through and the detectors underneath, what we've got is your X-rays will pass through, and then the position of that source changes and they'll pass through at a different direction. By taking all these images and sliding the body in, so we can do the same thing again at this position, for example, then we can build up a whole series of images, in each, shall we say, on each slice. So if we were investigating the head there, we could end up with 40, 50, 100 pictures. We could do the same lower down the body. And now that we have the power in computing, we can merge all those together. We can create a three-dimensional map of position of various structures within the body. Okay, so tomography is a very modern thing, and CAT scans are one example of tomography. Okay, they're all about producing 3D images. So that's true for all the systems we're going to look at from now on, or can be true. Okay, the basic idea is slightly less focused. Instead of actually trying to examine one spot, we take a bit of a beam coming through, a bit of a wide beam, and then what we do is, excuse me, get that fly out of here. What we do is pick up a very flat image, so we're not actually forming a picture, we're actually just detecting values directly opposite the X-ray tube. So where it's bright, where it is dark, where it's high intensity, where it's low intensity. As this spins around, different detectors will pick that up. So we have a 360-degree ring of detectors, and our X-ray tube is what spins around to take it at different angles. Okay, and once you've built up your image, then obviously you can do various things on the computer with it. We can zoom in, we can most usefully, we can color code it, because for human users it's much easier to decode colored pictures. It's much easier to see that. Okay, so we do use soft X-rays for this, we do use low energy X-rays for this, and the reason is you are taking an awful lot of images. So instead of one snapshot, this is hundreds and hundreds of snapshots built up into a film. Basically this is a bit like the wrong trousers, Wallace and Gromit type of thing. You're building up lots of images to make it look like you're moving in and out throughout the body. You have moving parts. Okay, so it does increase the dosage. Okay, however, if we turn down the power, we turn down the energy per second coming from the tube, then that semi-counters it. Okay, now similar system is not to do with imaging, but similar symptom here. If we're using radiotherapy, then that's kind of doing the same thing, except you're focusing X-rays. So actually you're having 2 or 3 X-ray tubes blasting a particular spot. How do you get the right spot? Well, you have to go through this scan first. Okay, you've got to go through this stage. So when you know the exact position, how far up the body, how far sideways and how far in, then what we can also do is use interference by using X-rays to treat cancers, kill off cancers and tumours. But this, for today, is just thinking about the idea of image. So, what's so good about it? Well, these are the kind of basics you need to know your way around, and it doesn't take a genius to kind of work through all these things, but it's one of those things you need to be clear of. Okay, so 3 main advantages of using these compared to an X-ray, a straightforward planar X-ray, a flat X-ray image. The first one is primarily it's a 3D image. Okay, the fact that it's 3D excuse me, means that you can then do a lot with it. So allows us, that is, to view key interest, whatever that interest is it a tumour or a break in a bone or whatever it may be, but the key is it's coming from different angles. So if you're seeing it from different angles, you won't get anything, for example, hidden round the back that you're not going to see too clearly, because you're going to image it from all angles, all sides. So build up in 3 from different angles, excuse me, so you can view the key interest part more clearly, but more importantly, pinpoint its position. Okay, so that's really important. Where exactly is it? If you tried an X-ray straight through, well, let's go back up to this image, for example, you can't see from this how far into the body this is. So if you are trying to do some microsurgery, you need to know exactly where you're going in from. Is it easier to come in from the back, for example? Okay, so pinpointing its position with accuracy is a very important thing. Second thing, again, not so much just for CAT scans, but anything going off to a computer, what we can do is the computer can manipulate the image. So it can play around with the numbers that represent the image cells, the pixels within it. So what you can do, excuse me, trying to talk and write at the same time, so try and manipulate the image, e.g. add colour, which is really useful, very easy to see, different organs in different colours, different types of tissue in different colours, or even remove parts, so e.g. remove the rib cage. So if you want to really investigate what's going on inside the chest and the picture is cluttered with the rib cage, then you can just basically erase them on your computer. Obviously not in real life, but the image of it, so your image is much clearer. The crucial other thing that's really important here is, because you're using low penetrating X-rays, a lot more of it is blocked off, a lot less goes through. However, you're adding multiple images on top of each other, so that increases the contrast between the different materials, even if the materials aren't much different. So basically it's more sensitive overall, the thing that you're detecting, to differences in density, in tissue density. Okay, and why is that important? Gives better contrast. Okay, so you know, those are all big useful ideas, really kind of crucial ones. However, you do need to remember what's the main disadvantage. Well, as it's a multiple picture, a composite image, so it's composed of excuse me, don't know what I'm writing there, as it's a composite image made of composition of lots of different images, and then what we end up with is the dose, the energy deposited in the body is higher. Okay. Again, they're saying not too much higher nowadays, but again, it's going to be a dose of is higher, so therefore more risky, more risk. Okay. I won't say risky, but you know, it's going to increase your dose. Okay, guys, that's it. Those really is the ideas behind our first section. That first section, obviously, the very first section is obviously how do we make X-rays? How do we basically get it to work? Fairly straightforward. Bit of revision in many ways over the stuff we've done. Then more importantly, once you've made that, how do you get the image from it? So your image and how it is all absorbed and the mathematics behind it, all of that kind of stuff is crucial. In terms of detail, however, the big picture is important with medical stuff. That's not a joke. The big picture being, how do we get the best images possible to find out what's going on inside the body and get the most from our expensive machine. Okay, so descriptive stuff, learn these, have a think about what they mean, because that makes it easier to learn, but there's some fairly obvious stuff in there. Really, really important, a common question about medicine.